Hi, my name is Professor Derek Gordon, and today's lecture is on the principles of probability. So some of the key terms that we'll be using are an event, which provides a set of outcomes. For example, an event could be tossing a coin, rolling a die. An event could be the gender of a child that is born. Another one of the things about regarding events is the outcome. What's the result of the event? So you can have, if you toss a coin, you can have either heads or a tails. If you roll a die, you can have either 6, 5, 4, 3, 2, or 1. And for if you have a child, then the gender of that child can either be, for example, male or female. Now, the probability we define as being the number of outcomes that fit our description divided by the numbers that are considered possible. So if you're flipping a coin, well, what are the possible choices? You either have a heads or a tails. So the denominator in this case would be 2. If you want specifically a heads, which is the one fitting our description, then that's 1 out of 2. Similarly, if we're rolling a die, as I mentioned just a second ago, there were 6 possible outcomes for the die that are possible. Well, 6 possible outcomes. And the one we're specifically interested in is the just rolling the number 6. So that's 1 out of the 6. If we have a child who is born from fertilization, it can be, we say it's either male or female, so that's 2 possible outcomes in terms of the gender, and we're specifying boys, so the numerator would be 1 out of 2. And last example might be if you have you have a 52 card deck, and you want to know what's the probability of getting a king in that deck? Well, the total number of possibilities, as we said, is 52. Any one of the cards is possible. How many kings are there? Well, there are 4 kings in a 52 card deck. So that would be 4 out of 52, which is 1 out of 13. So one of the important rules that we use when we're doing probability is something called the addition rule. So the addition rule answers the question, what's the probability that either event A or event B will happen? So that's going to be the probability of event A occurring plus the probability of event B occurring. The multiplication rule is what's the probability that the event A and the event B happen? Well, that's sometimes we refer to that as the joint probability, and that's the probability of event A times the probability of event B. So, one of the important questions to ask is, are the events mutually exclusive? So when 2 events cannot happen at the same time, they are considered to be mutually exclusive. So being a boy and being a girl is a mutually exclusive event. Being a freshman at Rutgers and being a junior at Rutgers is mutually exclusive. Being a boy and being a junior is not mutually exclusive. One can be a boy and a junior at the same time, so we would say that's a non-mutually exclusive event. So for the questions below, indicate whether events are mutually exclusive or not mutually exclusive. A, being the planet Venus and being the planet Jupiter. B, being a number that is divisible by 17 and being a number that is divisible by 19. So here's a sample question with the addition rule. Suppose we have 10 students in a class. 3 are seniors, 5 are juniors, and 2 are sophomores. There are 6 girls and 4 boys. What's the probability of being a senior or a junior? Well, as we talked about previously, using the addition rule, that would be the probability of being a senior plus the probability of being a junior. So there are 3 seniors out of 10. That's how we remember how we compute probabilities. It's the number fitting our description divided by the total number possible. There are 10 students, so the denominator is 10 in this case. 3 seniors, so that gives us 3 out of 10. Now the number of juniors, there are 5 juniors. So 5 out of the possible number of students is 10. So that's 5 out of 10, or 1/2. So if we add these two together, we get 8 out of 10, or 0.8. Now, what's the probability of being a boy or a girl? Well, there are 4 boys and 6 girls, and as we've stated, you can't be a boy and a girl at the same time. So for the purposes of this presentation, the probability of being a boy is 4 out of 10, and the probability of being a girl is 6 out of 10. And that's again using the addition rule. They're mutually exclusive. That's 10 out of 10, which is 1. In other words, everyone in this class is either a boy or a girl. 1 is the highest probability you can have. Now, what's the probability of being a girl or a junior? Well, the probability of being a girl is 6 out of 10, since there are 6 girls out of 10 students. And the probability of being a junior is 5 out of 10. We saw that earlier. And so if we add those together, we get 11 out of 10, which is a problem because 11 out of 10 is greater than 1. There's no way you can have a probability greater than 1. So why did that happen? Why did we compute this probability of being greater than 1? What happened was we double counted or overcounted. And what did we overcount? Well, we overcounted. We didn't take into consideration whether or not these two events were mutually exclusive. They are in fact not mutually exclusive, and so therefore we have to take that factor into consideration when we compute probabilities of non-mutually exclusive events. When we use the 6 out of 10 probability of being a girl, we're considering girls who are seniors, girls who are juniors, and girls who are sophomores. When we use the 5 out of 10 probability for being a junior, we considered for boys who are juniors and girls who are juniors. So you can see the girl and junior condition was counted twice. So we have to subtract off that number. So the probability of being a girl or a junior is equal to the probability of being a girl or being a junior minus the probability of being a girl and a junior. So that's 6 out of 10 plus 5 out of 10 minus 6 out of 10 times 5 out of 10, which is 0.8, which is a much more appropriate probability. So let's consider another question. Consider we have 2 violet plants that are heterozygous, big P and little p, for purple flowers. What's the probability that they will produce a heterozygous offspring? Okay, so we have big P, little p here, and big P, little p there, and that's the phenotype we get. We get a purple flower. So we want to know what's the probability of producing offspring that are also heterozygous. Well, we use the famous Punnett square to do this. Okay, so the probability that the offspring is a big P, little p is equal to the probability that the male flower gave a big P and the female gave a little p, or the probability that the male gave the little p and the female gave the big P. Well, the probability then that the offspring is big P, little p is equal to 1/2, right? Because a male can transmit one of the 2 alleles, either big P or little p, and so if it transmits the big P, that's 1 out of 2 possible alleles that it transmitted, so that's 1 out of 2. And the probability that the female gave little p is also 1 out of 2. She could either have transmitted the little p allele or the big P, and so that's the denominator would be 2 in that case, as it is here. But she transmitted just 1. This is the one that meets our description. She gave the little p, so that's 1 out of half. 1/2 times 1/2. Plus, and if you do you can check that you get the same numbers here if the male transmits the little p and the female transmits the big P. So you get 1/4 plus 1/4, which is a half. There's another way to do this. You can do it by Punnett squares, as Punnett showed. Each of these cells in this 2 by 2 table represent the result of transmissions of the values on the both the vertical and the horizontal sides. So in this cell, this is a big P and a big P were transmitted. Here, big P, little p is transmitted, and so this would be, say, this side here is male and this side is female. So you can see that out of the 4 possible genotypes that occur, there are only 2 that are heterozygous, and so that's 2 out of 4, or 1/2. So now we want to consider the binomial expansion, which turns out to be quite useful when doing probability calculations. When we have multiple events and are given the order of outcomes, we can use the multiplication rule. But what if we're given no order? Well, there's the long way, and then there's the binomial expansion. Okay, so suppose we have 4 children. What's the probability they'll have 2 girls and 2 boys? Well, we can count all the different ways that this can happen. So, for example, if we have 4 children, the 2 girls and 2 boys, you could have girl, girl, boy, boy. You could have girl, boy, girl, boy. You could have boy, girl, girl, boy. You could have boy, girl, boy, girl, boy, boy, girl, girl, and girl, boy, boy, girl. So it turns out that there happen to be 6 different permutations that would satisfy the probability of 2 girls and 2 boys. Now imagine if we had a family of size 10. Instead of listing all the permutations, we can use an easy equation to help us. If you use Excel, this is known as the combin, C-O-M-B-I-N function, and it computes all the combinations when you have A is a desired outcome and B is a remainder outcome. So if n is the total number of outcomes, then A plus B equals n. Okay, so in our situation, we have n equals 4. We have a total of 4 children. A can either be the number of boys or the number of girls. It doesn't matter. So we want, say, 2 girls, and B is the number of boys. Then this would be something called 4 factorial over 2 factorial times 2 factorial. The exclamation, as noted, it stands for factorial, and then this is the product of that number times all the numbers down to 1. So 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1, and the other 2 factorial is also 2 times 1. So you get 4 times 3 times 2 times 1, which is 24, divided by 4, which is 6. And that's the same answer that we saw previously in the previous slide when we counted everything. Now, there's one more thing we need to do to calculate the true probability of a desired number of a certain event. So if P is the probability of the desired outcome and Q is the probability of the other outcome, well, in this case, if we're talking about the probability of having a male child or a female child, it turns out that that's 1/2 for each. So the probability of having a boy is equal to the probability of having a girl in terms of offspring. So the probability of having 2 boys and 2 girls in a family of 4 would be this term, the 4 factorial over 2 factorial times 2 factorial, times the probability of, if this is the probability of having a girl, it's 1/2, and there are 2 girls, so we square that, and then it's also 1/2 for boys, we square that, and so then the total total calculation is 6 times 1/2 squared, which is 1/4, times 1/2 squared, which is 1/4. So you get a 1/4 times 1/4 is 1/16, so it's 6 over 16, which is 0.375. Question 2. How many ways is it possible for a family with 5 children to have 4 boys and 1 girl? So, you'll find a number of items relating to today's lecture in your homework assignment. On and one of the homework problems, in fact, has you use the binomial expansion rather extensively. It also makes use of the probability of multiple events.